Okay, let's solve another simple problem. Basically, all problems are simple, isn't it? This is a stick or a ladder, point A and point B. This angle is theta. This is a frictionless surface. So as we had the discussion before, that this stick is not going to remain as it is. It's going to slip. Point A is going to slip down, point B is going to slip towards right. And it is given that these 2 points don't leave the contact. They always, this point A always touch the vertical wall and the point B always keep touching the horizontal wall. So suppose the point A has velocity of v downward and point B has velocity u to its right. Then again you have to find the relationship between v and u. That is an easy job, so do it quickly, do it fast. I suppose you will get something like v is equal to u cos theta or u is equal to v cos theta. Let's work out and see what it is. You have to write a relation, constraint relation. Let's consider this as y, this as x. Now x squared plus y squared is a constant, that is the length of the ladder. Fine. Differentiate it. 2x into dx upon dt plus 2y into dy by dt is equal to 0. dx by dt is the velocity of this point B. So 2x into velocity of point B is given as u plus 2y dy by dt is it's not the velocity of A. dy by dt is the negative of the velocity of A because u is given in downward direction is positive. Now dy, the sign of dy is negative, y is decreasing, so dy is negative and dt is positive. Dy by dt is a negative number, so dy by dt is not the velocity, velocity is minus dy by dt. So this dy by dt is minus v, this is equal to 0. So from here you get that u is equal to v times y upon x is equal to v upon x upon y. X upon y from here you can see as tan theta. Oops, this is not cos theta, this is tan theta. And u comes out as v cos theta. So u is equal to v tan theta. What am I doing? U is equal to v into tan theta. Okay, so I hope you got this, tan theta, not cos theta. Okay, so things are working fine with you. It's easy, you're getting through this, no problem. Okay, let's solve a couple of more problems. This is a wedge kept on a surface, frictionless, smooth surface. The wedge is free to move, it is not fixed. And there is a vertical column like this. The smoothness, the angle of inclination matches. The surface of this column and the surface of the wedge, they come in contact at each point. And this column is allowed to fall down vertically. So it is constrained to move in vertical direction. It can only come vertically downward. There's a wall like this, and that allows the column to come only vertically downward. So the mass of the column is 2m and the mass of the wedge is m. So the column can come down only vertically downward. The wedge can go only horizontally. So the angle of the wedge is theta. So now you have to find the relationship between wedge and the column. Relationship between the velocity of the wedge and the column. So give some time to this. Think about it. Okay, so in this case, you have to use a little different concept. The thing is, suppose there's a wedge and there's a mass that is moving on the plane, and the wedge is fixed, only the block is moving. The block goes down the wedge. Now you have to appreciate that the velocity vector would be parallel to the plane. So the velocity vector which is perpendicular to the plane will be 0. The block will not go perpendicular to the plane at all, because going perpendicular to the plane means it is pressing and getting inside the wedge. That is not going to happen. The block will always move parallel to the plane. It cannot go perpendicular to the plane because normal reaction will oppose it. Going perpendicular to the plane, that means it is causing depression into the wedge. That is not possible if we are considering rigid bodies. So the block will always have velocity parallel to the plane, and the velocity component perpendicular to the plane is always going to remain 0. Now that is irrespective whether this wedge is moving or not moving. Even if the wedge is moving, the block or the column in this case cannot go perpendicular to the plane of the wedge. Going perpendicular means you are causing some depression into it. You cannot move perpendicular to this plane because the normal reaction is going to oppose the perpendicular motion, and nobody can have a motion in this particular direction. In this perpendicular direction, there cannot be any motion at all. So if there cannot be any motion at all, then the velocity of the column perpendicular to the block should be 0. Or the relative velocity of the column perpendicular to the block should be 0. Meaning, the column is like this. It can go in perpendicular direction, but when it goes into the perpendicular direction, the block itself moves like this. So actually the column has not caused any depression. It is due to the movement of the wedge that the perpendicular motion of the column is allowed, because the wedge itself is moving. But whatever perpendicular distance the column will cover, the same perpendicular distance the wedge will cover. That means if the column is kept like this, and this point on the column that comes here, then this point which is on the wedge, that should also come here. Meaning they do not have a relative velocity with respect to each other. Right? So in that case, there will be no depression caused on the wedge. That is the constraint of rigid body here. So the column should not go inside the wedge. For that, it is important that the relative velocity of the column and the wedge perpendicular to the plane of the wedge should be 0. So that's the concept here. So if we do that, and just to add a little bit on the understanding of this, suppose I want that the smaller block should not move relative to the larger block. That doesn't mean that it shouldn't move at all. All it means, if the larger block goes x distance, smaller block should also go x distance, so that when both have moved the same distance. So the smaller block has not moved relative to the larger block. So if this wedge is stationary, then the column should not have any velocity at all in perpendicular direction with respect to the plane of the wedge. But if they both are moving, then there shouldn't be any relative velocity. Similarly, like in this case, if this lower block is fixed, and I want that the upper block should not move with respect to lower block, then upper block should not move at all. If the lower block is moving, then the upper block should move with lower block. That means there shouldn't be any relative velocity of the upper block with respect to lower block. Fine. So in this case, the surface is smooth. The wedge will move. So the thing is, there shouldn't be any relative velocity between the column and the wedge in the direction perpendicular to the plane of the wedge. So that is the concept that will help us to find the relation between the velocities. So let's see. And I hope you're understanding the situation, what's going to happen. The column is going to drop down and this wedge is going to slide to its right. Everything is smooth, frictionless. That's what's going to happen. Right. So the column has velocity vertically downward. Fine. Because of these two restrictions. And the wedge is going to have velocity horizontally. So let's see, the velocity of the column perpendicular in the perpendicular plane, the velocity of the column perpendicular to the plane of the wedge. This is the column, this is the velocity vertically downward, and this is the line perpendicular to the plane of the wedge. This angle is theta from geometry. So the velocity component of the column, suppose this is coming down with velocity v, and this is going to its right with velocity u. Then this is v. The component in the line on the line perpendicular to the plane of the wedge is v cos theta in this direction. Now the wedge should also have the same velocity in this direction, only then there will be no relative velocity. The wedge has a velocity horizontally, u. This angle is 90 minus theta. So its component is u sine theta, right? So this is u sine theta. So the relationship between the velocity will be, velocity of column will be equal to tan theta into velocity of wedge. This is your required relation from the concept that there shouldn't be any relative velocity between the column and the wedge on the line perpendicular to the plane of the wedge. Fine.